Hi, everyone. My name is Kevin Limtow, here to describe my Project 3 system for measuring and transmitting the propeller speed of a simple motor system. So the system described in this project, again, as I said, is fairly straightforward. It's a combination of hardware and embedded software necessary to measure the speed of a propeller that's going to be driven by an Arduino. The speed of the propeller is going to be measured in rotations per minute. I'm going to use the term RPM from now on, using an infrared IR emitter detector pair. The architecture implemented by the Arduino should either be a round robin with interrupts or function queue scheduling architecture. For the purposes of my system in this project number 3, I'm using a round robin with interrupts. So this is really just derived from the assignment prompt itself. So the stipulated requirements, we don't have to go through all of these. The basic ones still persist from projects 1 and 2. We're going to develop it to execute it on Arduino, developed using C or C++. I've, again, as I said, elected to use a round robin with interrupts design. And for the purposes of collecting and displaying my data, I'm going to periodically transmit everything to a host PC, just over a serial communication protocol, USB in my instance. Derived requirements, I've decided to execute this on Arduino Uno, just because that's what I have available. I'm going to interact with the hardware via the serial monitor, just very basic. I'm going to have the application running on my Arduino Uno continuously and intermittently transmit both the timestamps of collected measurements as well as an RPM value of the propeller as it's spinning through the IR emitter detector pair beam path. And so the application is going to use a hardware interrupt to determine when the IR detector senses that low light condition, which is really just when a propeller blade breaks the path of light between the IR emitter detector pair. And because it's a round robin with interrupts loop, I have just programmed in a sentinel character to allow me to end the program. So it stops outputting serial messages. Getting into the design here, this is where things get a little bit more tricky than than the past couple projects, at least in my opinion. I struggled a little bit with this, so I'll describe some of the pains that I went through and the resolutions I had to take. So first and foremost, I'll just start with the motor itself. So at first, I was using a dual H-bridge motor driver chip that came in one of the Elegoo R3 project kits that you can see here. I neglected to actually use that at the end of the day, just because it took me so long to get the IR emitter detector pair working and calibrated for the propeller blades I was trying to sense. So I decided to just forego all of that code and hardware to control the fan speed, just because it was becoming a little too onerous. So I've opted to basically just hook up a simple DC motor. It's a 5-volt DC motor. It's a little toy motor. I can attach a fan to it that looks like this. I'll describe why one of the propeller blades is colored in. But that's the propeller blades on a DC motor with a basic round shaft. My Arduino kit came with a nice breadboard power supply module, which takes a 9-volt input battery and converts that down to 3.3 or 5 volts. I've decided to set my jumper pins so that it outputs 5 volts to the motor, so it's just running kind of at full capacity. I'm sure I could overdrive the motor, but for safety, I'm not. The main guts of the system hardware is the rest of this diagram. As you can see, I have an Arduino Uno that is communicating over USB to a host PC to transmit the data that I just mentioned, the timestamps and the RPM values. I have my IR emitter here in clear LED color that's emitting in infrared, and I have my photodiode here. The IR LED, it took me some fine tuning because I wasn't getting the amount of light that I needed through. So it took some fine tuning. I initially had a series resistor going to that IR LED, but because I wasn't actually getting enough light out through to the photodiode in my photodiode circuit, I actually took out that series resistor. So it's just running at full current capacity that the Arduino Uno can output. So normally that's dangerous for LEDs. I don't suggest that everyone does that. It's just that because I wasn't getting enough light output from that LED to get to the sensitivity levels I needed, I opted to forego that series resistor. The photodiode circuit is very straightforward. I have a basic pull-up resistor tied to the hardware interrupt pin, which is the digital pin 2 on the Arduino Uno that accounts for hardware interrupt 0. And so I have a pull-up resistor 10K value going up to this 5-volt line. So ordinarily it's 5 volts. When the photodiode starts to see light, it pulls that down to ground, and so I'll see a voltage drop. So anytime the propeller blade or some opaque object passes by my IR LED, it's going to reduce the amount of light going into that photodiode. The voltage is going to get pulled back up to 5 volts. And so it's going to go up. And then once that obstruction passes through and the infrared light is once again allowed to hit that detector, the amount of light will increase to that photodiode and the voltage level will drop. And so I sense that falling edge. So I hope I described that well, but that's just the basics of the circuitry. And then I have a status LED. Again, it took me a while to debug and troubleshoot this and get everything just right with the locations of the IR emitter and detector pair, and note that I actually had to point them to one another very closely. There's only about maybe half an inch of space between these two that allows the propeller blades to go through. Because it took me so long to get that working, I have a simple status LED that flags every time my hardware interrupt goes. So the interrupt service routine just changes the state of the status LED, so I know it's actually working. So that's the hardware design, and it took a little while to set up, and your experiences may vary on how well your IR emitter detector pair works with one another, but that's how I got mine to work. Again, pointing the emitter detector pair towards one another with just about a ½ inch of space in between. No series resistor on that IR LED, and a little pull-up resistor on that photodiode. And everything attached to, or that photodiode circuit attached to hardware interrupt 0 or digital pin 2. I mentioned the fan I'm using, the little propeller blades. They unfortunately have some translucent materials on the fan blades, just a translucent plastic. So this translucent plastic was not enough to actually trigger the hardware interrupt because I wasn't getting the voltage level to drop down far enough in the low light conditions when the blade would break. So I had to color one of these in just with a Sharpie. So that's why one of my propeller blades is colored black. And that's enough to actually trigger the digital logic level threshold, and the hardware interrupt senses the falling edge after it passes through. So the software for this is actually very straightforward. It's very, very similar to Project 2. There are 2 threads here, one that the user is taking on and one that the application is taking on the Arduino. I'll talk about the Arduino application. First, starting with the ISR. Right now I have that set as an interrupt on interrupt 0 or pin 2 of the Arduino Uno, and I have it set as a falling edge trigger. So every time it senses that falling edge on coming from the photodiode, it's going to increment a counter. And that's what I wanted the design to do. I'll talk about the implementation in a second, but essentially it increments a counter every time the ISR triggers. The round robin with interrupts loop that I have is set for a 5-second interval or 5-second period. So once every 5 seconds, the intent is for the loop to check for a sentinel character. If there's no sentinel character, it'll take a timestamp, calculate the RPM based on the counter value from the ISR. It's going to print a time and RPM out through the serial bus, and then it's going to reset the counter. And all the while, the user is, after they've set everything up in the hardware and opened up the serial monitor, they're going to receive the intro message, power the motor, move the propeller blades into position. And what I'm going to do is I'm just going to view the transmitted data over a 1-minute interval. to show that, yes, I can see an RPM calculation and I can monitor that and graph it out in Excel. Then I'm going to move the propeller blades out of position, power off the motor, and input the Sentinel character. So very basic, very similar to Project 2, where we had a timer interrupt and just outputting a serial output for temperature. This one just outputs an RPM calculated value. As I go through here, I'll start to talk about implementation now. So as I was just mentioning in the design section of my code, I did struggle to get this working. One thing I noticed was that this loop, this interrupt service routine, whenever falling edge was detected for whatever reason, I think as it was transitioning from a high logic level to a low logic level, I was getting a lot of bouncing in that pin. And so even a single trigger would cause or even a single blade pass, or, if I put my finger in between the IR path, I would get, tens of ISRs to execute. So my counter would jump up a bunch. And even if I just, put my finger in it once, it would say, oh, you have a RPM value of, say, 1300. So obviously, that was incorrect. What I needed to do was add some process instructions into that ISR. My initial attempt, or my initial thought, was to put a debounce code into my ISR, which I don't know if that's tremendously good practice to have, extra instructions in the ISR, but I found that this works. I'm not actually sure that it's doing its job as a debounce routine. I think it's just having extra instructions in the ISR seems to delay it just long enough to prevent the debounce, or prevent bouncing. At least that's my hypothesis. At the end of the day, the code works, and I'll show you my demonstration in just a little bit. But if you're wondering why my ISR has more code in it than just incrementing a counter, that was the sacrifice I had to make come implementation time, when I was actually testing things out and things weren't working as intended. So that's just what I had to run into. The other element to this is I have a debug section of code. Again, I have that toggled on for now, and that's connected to the status LED. It's just a red LED that I have. So whenever this ISR gets executed, it just changes the state of the status LED. That's actually I think I pulled this directly from CM Polymer's code. So the intent there is just to have some way of knowing whether or not the ISR is triggering, because everything else is in infrared. And that's basically it. So I don't want to go through every line of the code. I've described the application software in this activity diagram here. Everything executes as designed, just with a couple caveats for how the implementation actually needed to work for the written code to enable this all to work. So with that said, I'm going to go ahead and stop the recording here and shift over to my hardware setup, which I'll actually execute. Thanks, everyone.
Hi, everyone. So I'm just going to walk through my hardware very quickly, though I know I've just done that in the previous section to this video. This is the Arduino Uno, or actually it's the Elegoo Uno. I have my hardware set up here on a little breadboard. You can see the status LED is that red LED in the far back there. I have my infrared LED. It's this clear LED here. I hope that's coming out on the camera. And the black looking LED is actually that photodiode, and you can see just about a ½ inch of space between them. Not very much. I had to make sure that they were pointed to one another and very close by, so I could actually break the beam with this propeller blade when it passes on through the middle there. So you'll see that status LED go. I won't go through the nitty-gritty of the circuitry because I've already done that in the previous section of the video, but let's go ahead and get started. I'm going to go ahead and take my USB port going to my Arduino Uno to connect it to my host PC. You see power go on there. I'm going to start my serial monitor here in Visual Studio Code. So I'm going to go ahead and start monitoring. You can see I've already actually done it a couple times. So now you can see on the screen there, I've opened up the serial port, and every 5 seconds I'm going to get a timestamp value in seconds and an RPM value. Because nothing is breaking the beam, I'm just getting a value of 0 right now. And so to test this, I'm going to take my propeller blade and just break this IR path 5 times within a 5-second interval. 1, 2, 3, 4, 5. You saw the status LED go there, and my screen reported, or my Arduino reported, an RPM value of 60 rotations per minute, which is correct because I broke it 5 times within a 5-second interval. So I know the code is working. So now I'm going to go ahead and power my DC motor with this 9-volt battery here and power supply module. Now it's going, and I'm going to go ahead and introduce it to the beam, and we're going to go ahead and see the values on my host PC increment with an RPM value. And so I'm going to actually just let this sit for about 60 seconds. Just so I can get enough measurements and hope my hand stays steady. And then I'm going to go ahead and go through the walkthrough of taking the comma-separated value data and making a graph in Microsoft Excel. So I'm going to go ahead and cut the video here, and we'll go ahead and move over to the data analysis part of this video.
Hi there. So I'm back here now in Visual Studio Code. You can see here that this is the readout coming from my Arduino Uno setup that I had. It opens up the serial port, so just COM3. It tells the user that it's a propeller speed measurement, and it starts to spit out data. Saying, a time in seconds, number of rotations per minute. And so every 5-second interval, as you can see here in this column, I have a RPM value calculated and spit out. At about this 30-second mark here, that's where I broke the, occluded the IR emitter detector pair just by hand with the propeller blade. And I did it 5 times within a 5-second interval. And so that's how I vetted this code to make sure that that comes out to 60 rotations per minute. And so that is working as intended. About the 70-second mark, that's where I actually turned on the DC motor, started to get that fan in place between the IR emitter detector pair. And you can see the RPM values start to get calculated and spit out. And so for about a 60-second interval, between 75 and 135 seconds, you can see here that we got some pretty consistent measurements for RPM all the way through. At the beginning and the end of that measurement, that's where I'm kind of just taking the blades in and out, so it's not particularly accurate at those points. So you see here that towards the tail end, I probably in that 5-second interval took the propeller blade out, and so that's why you still see some RPM calculations, but that's just at the very end of the measurement. And so at the very end, I'd confirm that nothing is breaking the IR emitter detector path anymore. So RPMs drop down to 0. And I enter in the Sentinel character to end the program. And again, after a 5-second interval, it recognizes that and ends the round robin loop. So I'll go ahead and pull this data into Excel, and we'll go ahead and plot it. Everyone. So now I have all of this data pulled into Microsoft Excel. You can see that it was just comma separated value, so it's very easy to just set that as a delimiter when I open up the file in Excel. So now I can go ahead and take the values that I just collected with my Arduino setup, plot it out as scatter plot with lines, just because the lines make it nice to look at. And now I can see very easily that I have time here on the x-axis and rotations per minute here on the y-axis. And you see a small little blip here at the 30-second mark. Once again, as I was describing earlier, that's when I was manually testing that the setup worked as intended. So that should have been 60 rotations per minute, and I see 60 rotations per minute. And the RPM speed was actually fairly constant or fairly stable during the measurement interval when I had the fans in place. If I go ahead and reduce the range here on the x-axis, I can probably see just how much variance I was seeing. Let's bring this down to, oh no, let's bring that up to 4,800. And you can see here that it seemed pretty stable, oscillating between somewhere between 5,000 and 5,100 RPM. So I think that's a pretty good sign that my voltage regulator is pretty good, and the DC motor seems to be reasonably stable for a toy motor. And so that's what I have for you today. And I'll go ahead and post this to Canvas once everything is compiled. Thanks for listening. Bye.